Hello guys, today we will talk about the magnetic levitation. So as you can see in the video, how can we levitate a magnet and defeat a little bit the gravitation. So in menu, we are gonna talk about the magnets, Hall effects, operational amplifier. I use the LM324. What is an electromagnet, and the power of the MOSFET will be absolutely needed in that project. So in the circuit diagram, so this is the circuit diagram. It's very easy circuit diagram. We are feeding only with 10 volt. Separately, I use the L7805 to feed with 5 volt the sensor that we will talk about it. And then using a comparator, we attack the gate of a MOSFET. Here we will be talking about the sensor. It's the EQ733 that I use. It's an analogic linear sensor. We will talk about the Hall effect, which is the base of all this project. Then we talk about the electromagnet, which will be handling all this stuff at the issue of the project. So let's get started. To determine the polarity of the magnet, I use the compass. So we have the red needle of the compass is usually oriented to the north pole, north magnetic pole. So I'm using my neodyne magnet, and you see that whenever I'm switching it to different senses, the needle of the compass are changing orientation. So. And here you see evidently that the red one now is focusing to the north side of my neodyne magnet, which I will calibrate. So this way I need this orientation to deal with the Hall effect later and explain better the sensor. So here polarity is down. Hall effect briefly explained here. Whenever we have a piece of metal which is part of a circuit, so there is a current flow inside of it, we know that the electrons, they are flowing in the opposite direction, and we expose this piece of metal to a static magnetic field perpendicular to its surface. We can see that there is a force here pushing the electron aside. If this is side A, and here is side B, we see that in the side A we have a lot of negative charge. This means the density of charge at this side will increase, which also means that here we will be having less charges, so which means we can modelize it by positive charges. By the way, so the difference here, we will be having at the end a difference of potential, or a potential which is called V Hall. And that's what we will measure, we will use within our sensor. And here the Hall effect sensor, I used the EQ733. You can check its data sheet in internet. That's an analog and linear sensor. There is, of course, another which is digital. This means it gives or plus 5 volt or 0, and this we don't need it for our purposes, and we will see how. So that's the sensor here. Let me just put another color. For this sensor is presented here in this way. So we have here 5 volt maximum VCC, and here we have the ground, and here we have our output. So whenever this sensor is driven by a current I, so we have the current, and here is the sensor, the piece of conductor which is a p-type conductor. Okay, this is just for information. So we will see here Hall effect. So whenever here we put our magnet south north, we will see that when this south part of the magnet so go closer to the sensor, we will be having a voltage increase here, more closer, more voltage increase until we attain some saturation. And when we do the opposite, so north south, we get closer to the sensor, we will be having the opposite side, so voltage decrease until we get to this point. The maximum VCC load for that type of sensor is 5 volt CC. Hi. So here is the sensor. As you can see, I attached it to the, I gave 5 volt and then attached the output of it to the oscilloscope. And in this case, I'm addressing it with the north side of the magnet. You see, whenever this side of the magnet is near the sensor, the voltage decreases as per description, as per data sheet. The south side now, when I approach with the south side to that part of the magnet, so you can see that there is a voltage increase until the saturation of this is around something like 4,7, 4,8 volt. One important behavior not to ignore at all with this sensor, it's having two sides. Look here, I'm addressing the port, the north side of the magnet to the face. So you see that we have a voltage decrease. But if I take the other side, which is the south by default, to the opposite side of the sensor, you see that the voltage is decreasing also. We need to take into account when we balance between the magnet and the motor. That's the LM324. The output of the potentiometer will be at the pin number 3 of the LM324. This means at the positive, the non-inverting, you see I'm regulating it to be around 3 volt, something like around 3 volt from the beginning. At the pin 2, we see that this is the sensor voltage, it's around 2.5 volt without magnetic field, and here I'm triggering the output of the LM324. And the output is high because because the non-inverting side is low. And now when the south side of the magnet come near the sensor, you see that the output become low. So I want to take into account this, that I will be working with the south side of the magnet. This means from the other side of the electromagnet we'll be having the north one. So here is the circuit assembly on a small breadboard. So we have 10 volt, 0.687, even less than 1 watt. So, and the levitation is already there. You can see, you can take. Of course, here the cable and the things are a little bit disturbing as a first assembly. I see, and you see it's very stable. Hertz. It depends the frequency on the distance and of course the mass that this magnetic thing will carry.